Yeah, some of you have been here over the break. I have been already talking to Enkelejda, which is, I think it's great to have you here. We had a number of stations in life in common. She was doing her computer science study at the University of Stuttgart before I went there.
Yes.
And sort of we missed each other roughly by a year there. And then she went to Tübingen to do her PhD at the University of Tübingen, where she became a senior researcher in, I think, 2013. And then she was a junior professor since 2015. And since last year, she has a chair at the University of Tübingen, which is one of the hotspots with regard to machine learning in Germany. Her research interests are sort of at the intersection of eye tracking and machine learning, signal processing, with different applications. And I think we will hear a number of those things later in her talk. I have one thing which I like to share, and I to the comments or the chat in a second. She is the managing director or the head of Leaders Like Her, which is a organization that shows that leading by example by women. And I think it's quite inspirational. And so it's one of those things, a lot of people talk what we can do that more women go into leadership positions. And I think it's really interesting to see what's happening there. And it's quite a lot of interesting names. So I find that really a highlight. And with much further, I hand over to you for our closing keynote of Augmented Humans 2020.
Agresh, thank you very much for the nice introduction, and I'm really happy to be here, although virtually I would have loved to be physically there to also meet with this nice community that actually I didn't know before. So it's my pleasure to give this talk here today, and also the closing keynote, and hopefully to make you look at other people in a different way after we're finished here. So the talk, as the title suggests, is all about eyes and gaze, what we'll hear today. And actually, I would love to start with one of the favorite movies of my 4-year-old son, where I think it's a very nice example of an augmented human. A very inspirational example of how Hollywood thinks HCI might look like in the future at some point. And since it's the favorite hero of my son, I usually love to show this example actually over the talks, because it is quite a visionary example on what actually could be done in a perfect situation of human-computer interaction, but we're not there yet. All of this technologies and all of the way we interact with systems is basically motivated by the way we interact with each other. And if we look at a simple, very basic interaction scene, like here, a group-based interaction, what we found out is that people interact with the world multimodally, right? Through the parallel and sequential use of multiple perceptual modalities. And among speech, actually, gaze is one of the most important information cues for us humans. Just imagine how we share visual attention with each other. For example, when somebody in a room or somebody we interact with actually looks at an object, intuitively, our gaze will follow the gaze of our interaction partner and also look at the same object, right? Or in whatever interaction situations we are, reading the minds of other people and our interaction partners is very, very important to us. So for the last few years, I've been working a lot on how to make use of the information that we can communicate as humans by our gaze, and implement those information in some gaze-based interfaces or use this information to improve our assistive systems around us, right? So all of the information that we can communicate through the gaze goes back to some physiological restrictions that we have in our visual system. I don't know if you guys can see my mouse, but actually there's a very, very small area in our visual field where we can perceive information very sharply. This is called the foveal area, so 1 to 2 degrees. Just to have an imagination of what it means actually while reading. In a reading distance, it is just 2 or 3 letters actually that we can perceive sharply. Then we have a parafoveal visual area where we perceive information, though at much lower visual acuity. And then that's the parafoveal area and the peripheral area where we are sensitive to movements. Like if you look at this plot, for example, at an eccentricity of 5 degrees, our visual attention is just 30%, right? So that's why we actually have to move our eyes and our head to perceive the environment. So, but how to measure eye movements actually? No? So the most precise way would be something like this, which is of course very intrusive and cannot be done like that. That's why the state-of-the-art systems are actually some camera-based systems. In a very simplified way, we have something like a field camera monitoring the scene where we are, and we have 1 or 2 cameras in a binocular version recording our eyes, right? And after some successful calibration phase, we're actually able to map what we find in the eye images to the scene. So like mapping information from the eye image to the scene image, right? So thus sounds very easy. So we have a gaze information afterwards. The vision of my work actually, and all of that we've been doing the last few years, is some kind of pervasive gaze-based HCI, which means some combination of eye tracking methodology with state-of-the-art machine learning techniques towards pervasive gaze-based human-computer interaction, right? Having the gaze information always on in a way that enables us to interact smoothly with systems around us. What does it mean actually? So if we look at current trends in gaze-based HCI, we will find that most of the people and most of the research papers out there address some kind of multi-signal exploitation. So beyond the pure gaze information, people also use gaze and eye-related features, for example, blinks or pupillary information and so on. Also, there's a lot of work in the area of multimodal physiological computing, where we go beyond pure gaze, but also look at the face and the body of people, right? All of this information is supposed to somehow be used for truly intelligent interfaces, like gaze modeling for enriched user behavior, right? And in the sense that we're able to access and use this information not only anywhere, but also anytime. This is just an overview of some of the applications we're working on. So as you can see here, a lot of work has to be done to actually have very fluent and useful information and gaze-based information in driving situations. Then there's a lot of applications where we just move around and want to actually have gaze-based information in settings like museum, for example. What we've been working a lot is how to make use of eye tracking and multimodal physiological signals in the context of teaching. And this is just some work here showing our approaches on detecting automated visual attention hotspots just in a video-based manner. So just by solely analyzing videos, being able to detect where the visual focus of attention is. Other areas include the medical domain, where gaze-based interfaces can help to improve teaching. Like we see here, for example, in OPT dentistry education, or for eye-head coordination and eye-hand coordination purposes in neurological surgery. To be able to do that, I still like the figure that I want to use, or I typically use throughout my presentations, is kind of an iceberg demonstration. So what we know and what works very nicely up to now is something like in the lab eye tracking. And then what we want to have is this kind of ubiquitous eye tracking, so making use of the eye movement information anytime and anywhere. And in order to achieve this, we have to go through multiple steps. First of all, we have to have robust methods at hand to be able to extract the eye features in a precise way. Then we have to deal with calibration usability. So no user wants to calibrate multiple times, right? Just wants a quick calibration and wants the devices to work. And also after moving those devices, right? So taking off the eye tracker glasses or actually any data glasses that you might have in mind, and being able to just wear them again without explicit calibration. And the missing link there is that we, as a community, also have to provide actually interfaces, standardized interfaces and tools to be able to use those signals in the best way. I will talk today a little bit about methodology, so our work towards a robust and pervasive gaze-based HCI, especially in the realm of wearable eye tracking. And I'll go into two applications. One is the gaze-based assisted driving application. So I will show different approaches that we take to assist driving. And I will go into the realm of engagement sensing and teaching. So I will show you a little bit of our current work in using gaze information and also multimodal approaches in teaching situations. When we look at the methodological pipeline, typically users of eye tracking go through the whole pipeline. There's some time at the beginning where we go into feature extraction. So imagine you are in an outside scenario, you still want to have a robust gaze estimation, so you want to be sure that that you get actually the position where the user in the scene is looking at. Then in the next step, you want to do robust event detection, which means you are able to classify in an online fashion the type of the eye movements, meaning is it a fixation, so the stable eye movements where we perceive information, or whether it's a saccade, that is a rapid eye movements where we don't have the perceptual capability. And then still a widely under-researched area is in the realm of pattern analysis concerning the question of what is actually typical patterns in the viewing behavior that correlate with specific things, right? Think of, for example, expertise, domain expertise. So there is some methods out there, and I won't talk much about these things, but due to the complexity of the signal, there is still a lot of research to be done in making use of pattern analysis in an online fashion and being able to use those methods to improve the way we interact with systems. Let's look a bit at the feature extraction, right? So the users among you, the users of eye tracking and people who've used eye tracking in the lab, they probably won't face this kind of noise in the signal, but whenever we want to use eye tracking to assist driving, right? Observe the eye movements of the driver and give specific contextualized and personalized assistance, we have to first of all get the features in a robust way. That's why we've worked a lot to deal with all of this kind of noise, like reflections, occlusions, illumination changes, or physiological variations of the eye, to be able to get a robust gaze signal at all. This way, or along this line, actually, we've worked not only on data sets, so there's a lot of effort we've put here to be able to provide the community with a lot of annotated data sets. with different kinds of eye features, pupillary information, eyelids, and so on. And also in the methodological part, so for both the wearable eye tracking and the remote eye tracking scenario, and also have a few work on cycle guns, for example, to for data generation purposes, since it's always hard to ensure a variability in the data sets that we use for training purposes. And all of that has come together to different algorithms, just letting you know here what is like commercial state of the art in eye tracking. That is what you get here through the wearable devices. And this is the state of the art when we started back then, 2012, and then the state of the art that you actually had with the Pupil Labs wearables, not the glasses, but the wearables, and this is where we are now, right? So I think we'll have reached a point of saturation. So you see here the detection rate in relation to the pixel error. So the pixel error means the distance between the manual annotation and the detection made by the algorithm. So what is acceptable in most of the use cases is something like 5, and a pixel error of 5, of course, depending on the resolution of the image. And then I think we are now reaching 90%, which is okay. Yeah. So we didn't have the 100% coverage yet, but at least this is something where we can work with, or a reasonable actually result to work with for many applications. Here you see a different examples. This is work that we did together with Bosch for driver observation purposes, and starting actually from end of this year. Let's see what happens with Corona. Each of these, let's say, upper class cars should have a driver monitoring system. That's where we actually worked a lot in this realm to be able to provide case information and realistic driving scenarios. Here, of course, we have to use a deeper pipeline consisting of face detection, eye region detection, and up to pupil and iris detection. So this is just to get you into eye feature detection, what it means. Of course, we have still a lot of work to do in the realm of calibration utility. So typical calibration procedures, maybe you know some of them already use a 9-point calibration, where actually you have somebody guiding you through the calibration procedure, and it's okay, it's very nice, you can get very nice calibration results, but as you can imagine, this is something that is, first of all, time consuming, and this is something that the user cannot do on her own. You have to be guided through this procedure to get very robust results. So that is why calibration has been perceived and has been experienced as a process that is very annoying and very disturbing actually to the user. This is where we worked with a method that uses smooth pursuit calibration to do a very quick calibration that can be made by the user and is really providing the same results as 9-point calibration, though much more quicker, and can be done by the user without supervision, right? The method is called CalibMe. So if you want, if you ever thought of using some calibration along with eye tracking, you can just download the code of it. We also provide a smartphone version for that. So the calibration marker is on the smartphone. You just do some smooth. You just have to follow actually this marker, and the software will gather enough data points to make the calibration working. So another problem that we face in using actually eye tracking is the problem of slippage. And this is something where I actually didn't think of much. So I thought, okay, slippage is a problem when we started working with wearable eye tracking slippage is a problem, especially for us women with the hair standing in between the eye tracker and everything. But sometimes you just want to just remove the eye tracker and wear it back without having to do all of the calibration from the beginning. So, however, be careful wherever you use eye tracking to control for eye tracking inaccuracies also due to speech, right? So even when doing very small facial movements, as you see here, just like moving the eyebrows, will give you a very huge imprecision in the eye tracking, right? So let's go back to the video. I mean, you can see just some basic facial movement as moving the eyebrows will cause you a huge inaccuracy in your signal. To overcome this issue, we proposed last year a method called GRIP, which we've nicely actually evaluated with our collaboration partners in Lund, and it works some kind in a hybrid approach using some kind of an eye model, but also data-driven, and works very well for once the calibration is set, you can even remove the eye tracker without losing the eye tracking accuracy. So since we put last year for ITRA, we put a nice demo together, and I'll just let you view the video since I think it's very nice to get an idea of what you can do actually and what the gaze accuracy is. So that is our, let's say, our contribution to improving problems related to slippage. And the last actually link that we're missing towards all of these computational chains is having standardized interfaces, first of all, but also a lot of open source tools that allow us to work with different eye trackers, first of all, and have actually comparable results throughout all of them. So one software that we provide is called IREC. Some parts of our algorithms are also available with the Pupil open source software, but we also have our own software, which is very lightweighted, and you can even use with smartphones to do eye tracking in the wild. Let's look now at some applications where we use these information to improve either assistance functionality or even to explore different ways of looking at things. So the one area where I've been working a lot with is eye tracking and driving, so real world driving and making use of the eye movement information to improve particular functionalities in the cars. In this example that you've been viewing here is a scene from a crossing scenario. So you will see at some point an hazardous object coming from the left side, which is very hard actually to be seen because it comes actually in the dark area and it's a very low saliency. But if you look at that, could be something, a situation where you have probably to assist the driver or to inform and look at the ways of particular assistance or personalized assistance first of all. This is a project we are doing with Volkswagen Research, where we actually have a world model of the scene based on the sensors that are on the cars. So we have, for each of the objects on the scene, we have an idea of what kind of object it is, what's the extension of the object on the scene. So this is our world model from a multi-sensor fusion. And on the other hand, we have a driver model that is considering visually related features about the driver. So we can compute two scores based on those. The one score is the awareness of a driver for a particular object on the scene based on the saliency of the object and the driver model. And also we have a criticality, computer criticality to each of the objects on the scene based on the scene situation, right? And also on specific features that are related to the driving scene. So for the particular objects on the left side, you see there is a very high criticality but low awareness. So this is a situation where we actually could use head-up displays to augment information about the object that is probably to be overlooked. So in this area, we're exploring the usage of full-screen head-up displays to make a contextualized assistance to the driver, and we're exploring ways of guiding the attention towards specific objects on the scene. So this is kind of the work that's currently ongoing. So we are in some user studies with them to explore ways of guiding attention in a way that is subtle to the driver, so it's non-intrusive and does not actually disturb the current working process. Most of us think that okay, we're somehow on the trend of moving to autonomous driving. So the next step would be actually to look at ways of keeping an eye on the user or on the driver in conditionally autonomous driving scenarios. Why that? Because although we speak a lot about autonomous driving, there is still a long way to go to have systems that are robust enough to work in all of the possible situations, right? So we have to come up with solutions that enable us to operate in conditionally autonomous driving scenarios. What is that? This is a situation where the car drives most of the parts on its own, but sometimes for whatever reasons, the driver is still required to take over some driving situations. So together with research labs from Daimler and Bosch, we have thought a lot of what is like potential use cases that the driver could be occupied with during driving, during conditionally autonomous driving. And yeah, first of all, I mean, most of the use cases are around using tablets or handhelds in the car. So we've been specifically looking at what is the information that we can retrieve from the driver since we don't have any driving related input anymore? What is the information that we can infer from the eye movements? Does it allow us to actually predict or to classify the secondary task the driver is occupied with? And what can we do with this information? So the first study we ran here included 73 subjects in no longer driving sessions in a simulated environment, but the driving simulator is now state of the art with a car being put inside and full field of view vision, so very sophisticated, and we'll let them do actually 4 tasks. So the one task is just like being idle, looked at the eye behavior, the eye movement behavior in the idle task. The driver was not told to do anything specific, we're just like looking around. Then we had people watching a video, we had a reading task, and we had just like emailing. And just by looking at the eye movement signal, we were able to distinguish between those tasks. So you could easily tell whether the driver is occupied with anything or not. And then you can see here, right, okay, you can detect whether somebody is reading. Why? Because we do specific visual viewing patterns when reading, typically from in our culture, from the left to the right and then to the next line. And you have some kind of diffuse looking behavior when looking at videos and email. So there is a lot of information that can be obtained about the driver just by observing the eye movements. Then in our further work, we actually combined the information that we get about the secondary task based on the eye movements with the eyes on road gaze behavior and an assessment of the traffic situation, some state-of-the-art methods to assess the criticality of a traffic situation, put all the information together to classify some kind the takeover readiness of a driver, right? So from high takeover readiness to low takeover readiness. And in the case of a low takeover readiness of the driver, we used to augment the information on the scene and put a warning for the driver to actually make the driver look at the scene, right? So this already is enough to increase the takeover readiness and to make the transition between automated driving and manual driving go smoothly. The other area that I'm going to talk a bit about is how to make use of all of this new technology and the eye movement specifically in teaching situations, right? So this is a kind of a group teaching situation where you have the teacher teaching a small group of students, and we have recordings here. The first question that we wanted to look at was, how does visual attention distribute in such a group setting? So for that purpose, we developed a method that is able to do a semantic mapping of the gaze to the faces in the video. So all the faces are extracted basically here. They are clustered, so all of the faces in the video frame. So for each frame, the face is detected. They're all clustered, so we can make the faces to the ID, and then we actually make the gaze to the ID. And you can see here, we were able to see where does the teacher attention direct to actually with respect to each of the IDs. And we also looked at attention distribution toward genders, right? Just to be able to give the teacher some feedback mechanism on how does the attention distribute when teaching a particular subject to the ideas involved here. And for some of the subject related or for many actual teaching situation in technical subjects, maths, computer science, physics, whatever, people are interested in seeing also the attention distribution of the teacher towards the gender. So this is kind of a nice tool that we give them at hand for teaching purposes so they can analyze their own viewing behavior. This part of the work concerns more like the distribution of the teacher's attention. On the other hand, we can also look at the students. So what we started to do is something like using appearance-based eye tracking and the visual behavior of subject to see where is what is kind of on-task and off-task behavior. In this example, you see everybody was looking away from the material taught actually in front of the classroom. This is typically a teacher-centered situation. So we don't have any, actually any Pinocchio noses going to the screen. And in the other example, we have some visual attention directed to the teaching material. So this is some kind of automated analysis to look at on-task and off-task behavior in a specific context. Right? Let's look a little bit here in more detail. So we have all of the faces here, and we have few people actually who do not look at the teacher or do not show the same behavior as others, but probably take notes on something. So what we'd like to come up at some point is providing the teacher with a so-called attentive interface that looks at attention, at the distribution and the evolvement of the teaching attention, attention level during teaching situations, right? In that particular example, one discussion point from our side is actually, so we're classifying, for example, these two people as having off-task behavior, though actually we have a lot of discussions here, especially with this subject, saying, okay, is this really off-task behavior? So they're taking notes, and notes are related to the teaching context, but actually the teacher should be able here seeing like, okay, these two people are off-task, are taking notes, so I should just like lower my speed, right? Or at least wait for those people to take the notes, because while they're writing, they're probably not getting the content that is taught. So what did we do for that? I'll just show you a few of our first results on this studies, because it's quite interesting. So we had a lot of state-of-the-art machine learning models and our own developments on that to extract all of the faces, map them to the ITs. We went in a multi-model approach, so extracting facial expressions, eye and gaze, and also the head point, so extracted all of the features, and also let those videos annotate by experts, so 3 raters. We have 3 raters that annotated each of the students with regard to the on-task and off-task behavior. So you see here some of the features that correspond or correlate with on-task behavior, and the others that make up off-task behavior. And we trained some computational models to estimate the manually annotated engagement level, like support vector regression, for example, and recurrent neural networks. And we were able actually to reproduce the results of the driver, of the raters, and have an engagement assessment for each student, right? So overall, in the pilot study, we had 4 seminar sessions going on with 52 students. The task was to predict the level of engagement based only on the visual and attentional cues, and look at the synchrony in the classroom, right? So, and the synchrony was defined in the specific setting in the teacher-related or teacher-oriented setting as the similarity of visual features and body language between neighbors, right? So they were sitting 2 by 2 neighbors. So we actually looked at synchrony with regard to the neighbors. So when we analyzed those data, we found out that there is high correlation between what we get out of the visual features with the manual ratings. And this correlation increases when we consider the neighborhood information, which was very insightful to me to think of, like the recommendations of my mother during my school time, saying do not sit next to troublemakers, and apparently that holds, right? So people who pay attention to the lecture usually sit close to each other, and others, so like unengaged behavior seems to actually also infect the people sitting around us. One question that I'm always asked when I give these talks is actually how we deal with the data, right? This is a lot of student data that we're collecting. By the way, we have a lot of data that we recently collected in schools. So we have, apart from seminar students, like university students, we also have school kids through different grades, and all of the data, terabytes of data that has to be analyzed, and we're looking currently into those data. And when we went to schools to collect the data, parents, school directors, so headmasters, they all ask the same question. So if we have any people in the classroom who do not want their data to be used and to be recorded, how shall we deal with this data, right? So how shall we deal with those persons? So if we take these persons out of the classroom, and we rearrange the seating order, then we get probably something that is not close to reality, right? So we want the people to be in the most realistic scenario where we collect the data. Otherwise, if we take out like 5 to 10 people from the classroom, then this is not the real teaching situation. So to deal with this issue, we developed a framework for automated data anonymization. So there's basically 2 modalities that we work with, the visual features and also speech. So the visual features, for all of the IDs that didn't want to participate in the study, we had to anonymize the faces in the video material. And also a very difficult problem is to anonymize the speech, since our audio signal or speech is very a biometrical signal. We have to take care here that not only the part where a specific person which does not want to be recorded speaks, but also we have to take care of all of the indirect references to this person also are removed from the signal, right? So when, let's say, like Lisa is speaking and we know Lisa doesn't want to participate in the study, we have to anonymize all of the parts in the audio signal, but also we have to remove all of the indirect references to Lisa, right? The teacher asking Lisa to reply to some questions, or any people talking about Lisa being the person who has to do something, right, in a teaching situation. So with regard to the faces in the video material, we basically have 2 options, either to occlude those faces or to swap those faces. We actually decided to occlude those faces. This is an example of a teaching situation. This is just freely available data on YouTube, where we see this is, I'll go back to the beginning. So you see, this is the face that we want to anonymize, and we find this face through all the second student. So we find those faces and we anonymize those data. Of course, this rectangular shape here can be larger, just like for the demo purpose here. So we can actually parameterize the area around the face that has to be anonymized. For the audio speech, we have to take a little bit of more steps to go. So first of all, we have to silence speaking of the students that we have to anonymize, as I said. And we change actually to do that. We use a framework of state-of-the-art machine learning methodology, RNTipNets, to change the acoustic parameters of the voice by keeping the speech but protecting biometric traits. And also we have to take care of the indirect links to the person and find proper nouns and either change or silence them in the audio signal. As you see here, being able to use all of this information in very simple or naturalistic world, real world scenarios, can give us more information on, for example, if we use eye tracking and visual features in teaching situations, this can help teachers to improve teaching aspects. So they can have like really nice tools to work with. Think of like teaching teachers, right? So what is, or investigating questions are what is good, a good teaching way. So we can give them tools at hand to do this research. And on the other hand, it would be nice actually to have tools working in real classroom-based settings, or even for group situation where we analyze visual interaction partners and visual interaction patterns to find out how does, for example, leadership in a group emerge, right? So how do people efficiently interact in each other in group work? So this is all questions that we're currently tackling with people from educational psychology, and I'm really happy about this project, though data collection and so on is really long-lasting. I think we have learned a lot during those projects. Other areas that we work in is gaze-based interfaces for VR and AR. So I think with new emerging technologies, VR and AR, we can make a lot of use of the eye tracking signal to improve not only like the way we interact with those interfaces, but also make a personalized actually experience. So enable personalizing experience in VR or AR. And also improve to or contribute to resource saving mechanisms. A lot of actually people in the community look at diagnostic interfaces. So just by looking at the way people move their eyes around, you could in principle be able to analyze a lot of, let's say, like visually related diseases. And on the other hand, this information could be used to make personalized rehabilitation interfaces, right? So if you know, like, for example, here in this example, we have a visual field defect in a specific spot of the visual field. If you actually could use this information and make, for example, in VR or AR, make a specific gait guidance to the subject, this could lead to an improvement on how they actually scan the visual scene and their surrounding, and make them actually be undisturbed by this visual field defects in their real life, right, in their daily life. One question that I've been fascinated by is being able to find measures that speak for expertise. So the so-called proficiency-aware interfaces, and for example, in medical teaching, or also being able to infer the visual attention even without using specific hardware as we use now for the moment, eye trackers, just looking at video material and being able to make an assessment of, or gaze-based estimation actually in scene context without specific use of the hardware, just be webcam-based approaches. And a lot of potential for this technology is actually considered in the area of surgery, where eye tracking can be used actually to improve the ergonomy of those systems, right? So we have developed together with SAIS a gaze-based focus, let's say, adjustment of such surgery of equipment. Because for the moment, the surgeons, they just have to adjust their visual focus actually manually, which means they have to actually interrupt the surgery procedure to readjust their visual focus, while that could be easily done in a data-driven approach, right? So they have an ergonomic, an improvement of their ergonomy. So I hope to have given you a very good overview of what can be done with gaze. And I hope you look at people around you in a different way after this talk. I'm happy to answer your questions whenever I get to see the chat. So I hope it was some kind of an inspiration to look at the signal in a different way, and also to see like people working and tackling all of the challenging real world scenarios. Thank you very much. So thank you very, very much for having me here. And it's also time to say thank you to all of our collaboration partners and my group in Tübingen, which has grown quite large in the meanwhile. And I'm happy to take your questions.
Thank you. So maybe I start. I have a more general question about what the research is about. And I think your keynote gave a really good overview what you can do with eye tracking. And one common joke we make at our lab is like when somebody does eye tracking research, they're saying it since 30 years that eye tracking will be available everywhere. Eye tracking will be ubiquitous, like the mountain you have showed with the lines, and then at the top you have ubiquitous eye tracking. And just asking about your personal opinion, what do you believe does it take that we really go the step towards ubiquitous eye tracking?
So I'm I think we're very close to that. So actually, I mean, like you said, the technology has been handled as the key enabling technology for VR and AR, right? So there's a lot of applications in VR and AR which can be enabled by using those information. So for the moment, I mean, we have all of these devices going around, and you can see like we make use of this signal for in very specific domains, and there is products using the signal by Bosch and Daimler already in cars, right? So there is things going on beyond the research context, and actually for the moment, you're right. The community is kind of very distributed. You have all of these commercial solutions, which make it hard for the user to access them, right? So if you are about to give like thousands of euros to buy such a device, right, you're probably not going to use that much often. So it's both like, okay, the hardware is not there yet, right? So we have all of this like isolated solutions, and we don't have like standardized things to be just like wearing on like the glasses, for example, and we have different integrations even for VR and AR. So this is kind of fragmented stuff from the hardware part, and also from the software part. There is still work to be done to get this ready to use, right? If you think of a normal user, right, we have all those, like let's say a psychologist, they don't want to care about how to process those data. So it's just like still a lot of stuff that has to be done there to provide tools that just work to make this accessible to the user.
And coming back to this, I think there are
one question. I think we have recently seen quite some discussion about face tracking, and that researchers have said, we are stepping back from this because this creates a world where we don't, basically where we lose control. And I think now looking at eye tracking in combination with facial recognition, you get much more than who it is. You get a lot of intent, and I think you had really good things like the classroom. So obviously, sort of a lot of social protocols we can now quantify. A lot of things I can tell if somebody is interested. I can sort of tell a lot about social behavior. Do we have? And I think there is at the same time a lot of effort to put stuff into open source, which I personally think is a good thing, but at the same time, is it basically putting a massive weapon out there what people can use against us?
Yeah. So my remark is on this, that we as a community also have to take care about this data. So there's a lot of work that we are doing. Actually, you can imagine like all of this data collected in the car, where does it go to, right? So if I have a car that is being used, for example, by multiple users, car sharing, right? So, and I'm observing the user there, I'm observing the drivers there, I could even come up with personalized policies, right? Insurance policies. So you can think of multiple scenarios that can be suddenly enabled just because we have the data. So there's a large part of the eye tracking community is actually working on methods to ensure data privacy, and also do we like differential privacy, for example, for the eye tracking signal. in combination with face tracking, yes, I agree with you. So we have a lot of behavioral data about people, right? In the context that we're moving, especially in the educational context, we have to take care of this data and be very aware of what that means. That is why, for the moment, we actually do not provide any offline storage solution for all of the data that we capture. We just compute at the aggregated level of, okay, what is the attention level of the classroom? So to give the teacher some kind of a feedback about where is the moment during teaching where the attention drops and why, right? To just not provide this information or make this information accessible to everybody. But we had these problems when we asked, like when we were in the large scale study in schools, there was a lot of parents actually asking all of these questions, right? At some point when you can observe your people at a very detail, then there's no need to write exams anymore, right? So there's always like some benefits and also some drawbacks that we get with each of the technology. I think you have to raise the awareness of how to use this. And the approach that we take for the moment is that we do not provide like this detailed information at the user level. Just more like the data is not there to be like post-experimentally analyzed by everybody. I can see the chat. I don't know if there's more questions or not. Yeah. So
there are no more questions from the chat. Does anybody has questions now?
Yes, if I may, I have one. Can you hear me?
Yeah.
Good. I have a question. So
can you quickly introduce yourself?
UIs using eye tracking, and I was wondering, I think there is different ways of building UIs with that. In a way that I could see, for instance, having the UIs directly in the face of the user, or maybe having some other types of feedback. I'm wondering, do you see one way or the other? Do you think that we should go one way or the other? And also, if we had always augmentations of the eyes in a way with information all the time, would that make us look in different ways in a way? Like I could picture, for instance, if the system is failing and I'm looking for an information, I can see that the system is not recognizing what I'm doing. I could use some kind of sagat to kind of update the system and maybe force it to do something.
So this is like two parts of the question. The one is we humans, I mean, you see like also when Googling, right? So we come around and actually develop a way of dealing with systems around us. So we kind of know like also how to manipulate those systems. So for example, in the driving, I always take this example because everybody drives, right? So if you have a system that it constantly, like for example, the blind spot assistant. I don't know if you have ever been in a car where there's a blind spot assistant and it constantly warns you, right? Whenever something is in the blind spot. And after some time, you just don't look there anymore. It kind of captures your attention. So it actually drives a saccade towards them because it's some kind of movements in your periphery. So you tend to look at there. But okay, sometimes you get used to that. So the question would be not only using the eye movement information. So what I think is challenging here is also to get the semantics of the scene and the context, right? In any kind of augmentation scenario, the challenge is to actually being able to deal with the context and what is the user requirement for that specific context, right? So in some of the expertise studies, for example, for medical image viewing, we have seen that if we just augment the doctors with the scan path of an expert, they kind of, don't want to look at those locations because they feel like they're told to not be having an expert viewing behavior. But whenever we do this, let's say like guidance, very subtle, so they don't see some specific marks, but we only change like contrasts information in the image. They'll look at there, but they're not like, they don't have the feeling of being like kind of, told they're not expert enough to look at that. So the challenge is for many other augmentation scenarios. I think the challenge is basically getting the context and having the intent and the needs of the user right, and then augmenting.
Thank you.